Probability density function, PDF, is a statistical expression that defines a probability distribution, the likelihood of an outcome, for a continuous random variable x. Z-scores are a numerical measurement that describes a value x relationship to the mean in standard deviations. We'll be exploring the impact of random values and sample size on a continuous normal distribution. I theorized that as the sample size of random numbers increases, the maximum value for the random numbers and extent of the random distribution tails will increase. In other words, the more samples, the more likely we are to sample the very small and large numbers constrained between 0 and 1. To test this, I've created an experimental data set that has 8 sample sets of random numbers with sizes ranging from 100 to 1 million trials. And for each set, a normal PDF was made which uses the random values. Theoretically, there can be an infinite number of values between 0 and 1, but just keep in mind that you can always add a 0 or a 9 after the decimal, and the numbers will continue infinitely. But Excel has limits to the scale and precision of numbers. The Excel workbook tests this limit. We'll now switch over to the Excel workbook and take a look at these expected outcomes. So let's take a closer look at it. In the blue, we're looking at the maximum of the random values that are generated. And here I have annotated the top for 100 samples, 500, and so forth on to 1,000,000. The orange line, we're testing the extreme right of the normal distribution. So these are increasing and it's getting up to over 250. Notice that I've generated the normal distribution using a mean of 100 and a standard deviation of 34. The normal distribution uses the random numbers to generate the normal distribution. Let's take another look at the random data. I have the Excel workbook set up for manual calculation because of the large number of calculations involved. And every time I hit Shift F9, it recalculates the random numbers and the normal distributions. So in this experimental data, once again, we start with 100 samples and calculate the normal distribution. Do this same thing for 500 and so forth on to 1,000,000. I want to run this a few times, and what I want to look at as we do this is I want to look at the stability. Here you can see that the value generated here for the random number has diminished quite a bit, and it will change every time we run the calculation. I find that it stabilizes right around 10,000. So let's run this thing a few times and watch it. Notice how the values between 100 and 1,000 vary quite a bit, as does the 5,000, but not to such a great extent, and I find that it usually stabilizes right around 10,000. The other thing to notice is the table over here to the right, where I show you this number of samples, the random value that's generated, at least the maximum random value, and the maximum of the normal inventory. And here's the z-score. This tells you to how many standard deviations these values are. And what I want to look at in here is two things to notice, is that the z-value at about 10,000 is usually about 3.5. So if your sample size is 10,000, you can expect your maximum tails to your normal distributions to go out to about 3.5 standard deviations. And for 1,000,000, sometimes these go up to 6 standard deviations. Also, the z-scores can invert up at some very high levels. So again, let's run this thing a few times and watch those numbers. Notice here how at 100,000 trials how the z-score has inverted. And the same thing here at 10,000. So you can see that to get a stable distribution, you need to be at least 10,000 observations. The other thing that I want to point out is over here on this last table is that we normally in Excel only go out to about 14 digits after the decimal point. Here, so the actual precision of the number is 15 and the scale is 14. And here we're just looking at the min and the max.